Let and start talking electrical basics. This is a PowerPoint presentation I put together some time back. You got electrons, and incidentally, the outer electrons are the one that carries the power. Like when you got electricity flowing, the electrons are actually, it's sort of like billiard balls. If I lined up a bunch of billiard balls on a table and they were touching each other perfectly, and I fired my cue ball and it hit the one on the end, what's going to happen? The one on the opposite end is going to leave, and the rest of them are going to stay right where they are, right? That's just how that works. I mean, that's an inertia thing. But when the electrons jump from one valence ring to another on atoms, it flows like that. So, and where does the current flow in a wire? Does anybody know? Where does the current actually flow? If I showed you a piece of copper wire, where does the current flow? It's on the outside of the wire. It doesn't flow through the center of it. It flows on the outside of it. Okay, so you got your atoms here, and the electrons are a negative charge, and the nucleus of the atom has got protons. And you learned about this in school? Anybody familiar with this? You know about atoms and protons and neutrons? Negatively charged particles called electrons around the core, and they're whirling around it really fast. Electrons in the inner orbit or orbits are known as bound electrons. Now there's the bound electrons don't move, but the only ones that move are on the outside, right? The ones in the outer ring are called the free electrons, the valence ring. And if there's 3 or less free electrons in the valence ring, the material makes a good conductor. So if you've only got, how many electrons do you think gold has in its outer valence ring? 1. Only 1. If it has 8 electrons in the valence ring, it's a conductor. I mean, that's what insulators. I said the wrong word. So if it's got glass or wood or anything with plastic, something you're going to use not to carry the juice. But if it's got 4, it's a semiconductor. Diodes, transistors, they're made out of this stuff. Got that? Okay, so gold and copper only have 1 electron in their valence ring. That's what makes them such a good copper kind of has a tendency to corrode, though. But a material with 4 electrons in the valence ring is a semiconductor, such as the materials used to make diodes and transistors. So a semiconductor conducts, but only under certain conditions, right? If a valence ring has 5 or more electrons, it's an insulator, and one with 8 is a perfect insulator. Now, you guys have seen sparks pop, right? Whenever you see a spark plug wire popping, what's that pop? Why does it pop? You got any idea?
It's traveling to and from.
It's actually punching a hole in the air, and that makes that pop. So that's what thunder is, when lightning punches a hole in the air. It's kind of like, how many of you heard a sonic boom from a jet? That's the same thing. It gets going fast enough, it makes a vacuum behind the jet. Boom. That's the same thing as thunder. That's why it sounds so much like thunder, because it's like when lightning punches a hole and it disappears and air rushes back in, you got a thunderclap. See what I'm saying? That's what they're talking about then. Okay. Electron theory says current flows the organized force movement of free electrons in a specific direction. Continuous current flow in this one direction is known as DC current. If I've got my power and ground hooked up so that it's always flowing the same way, that's direct current. It starts with a 0 baseline and everything happens above there. If it's if it's alternating current where you're swapping the leads back and forth like your own power windows or something like that, or like on this sensor right here, actually is going to create an alternating current sine wave. That wave is going above and below 0. So 0 is the center line on alternating current, and it's the baseline on direct current. All right, so that's what I'm talking about here. We got alternating current here. A good conductor has got a lot of free electrons. Okay, so they're going to transmit electricity. We're going to go pretty fast on this. Electromotive force is caused by a difference in the electrical potential, and that's measured in voltage. So what do? You're going to take, when you're charging a battery, you're going to pull all the negative charged electrons. Well, this is what's actually moving to cause your power to go, and you're going to move them all on one side of those plates in the battery, and they want to go back to the other side. They have a desire to go back to the other side. They're trying to get back to the other side any way they can, and if you provide a path for them to get back to the other side, that's the path they're going to take. If it's a piece of wire, like what happens here, Brandon can answer this question. If I hook this up to both sides of a battery, what happens to the jumper wire? it becomes a load. It turns into a little smoke bomb. I don't know if you've ever noticed this or not, but a piece of wire, this one here has actually been heated up one time. I can see where it's melted off there. But anyway, you can take a piece of wire that long, and if you short something out so that it burns the insulation off a piece of wire, it'll fill a whole car up with smoke. One little piece of wire to fill a whole car up with smoke. And it ain't really good to breathe that smoke. You need to probably roll the windows down because it's poison, you know. But the fact is, one little tiny piece of wire will fill that car up with smoke. You know how much smoke an airbag makes when it lights off? We lit one off in the parking lot out when they filled the whole parking lot up with smoke. Jumped 10, 12 feet in the air. I got a video of it. But anyway, that's just a little smoke tail there. All right, there's the pool ball, the billiard balls. You see the billiard balls? All along the surface, it's felt all the way through. Some older cars and heavy equipment have their positive battery terminal connected to the chassis or the frame on the negative side. And the negative, see they got this one here with positive ground. Caterpillar Equipment Lab. If you're jumping off a Caterpillar, let me ask you this. If I've got a Caterpillar pipe loader and an International Huff, and the Huff has got positive, you know, it's got negative ground, and the Caterpillar's got positive ground, can I use jumper cables to jump them off? Actually, you can as long as they're not touching. If the bodies of the two of them are touching, then you got a short. But if they're not touching each other and the cables are long enough, you can do that. Oh, something else I was going to say about atoms a while ago. If you brought the nucleus in an atom up to the size of a golf ball, the nearest electron ring would be 3 miles away. Atoms are mostly empty space. But the difference between the size, I mean the actual matter in an atom and the empty space is like the difference between 1 second and 30 million years. Think about it, all that empty space you got there. Now we're all made out of atoms, that's how stuff feels solid, but atoms are mostly empty space. Okay, let's move on before I talk some more nonsense. Okay, today's vehicle has their negative battery terminal connected to the chassis. Everybody knows about this. You're hooking it, it's hooked to the ground. Where's the ground that leaves the battery go? The big ground wire that leaves the battery, where does it usually go?
To the bottom.
The body and the engine block. The body's got to be grounded, the engine block's got to be grounded. Whenever you don't have grounds, that current goes strange places and does strange things. We used to have these motorhomes that would come in here, and the motorhome was basically an F-53 chassis. They had a motor coach put on it. And these people would take these big, heavy, double-aught gauge wire with big, heavy copper on it and just run straight from the frame to the engine. Not that far. This wouldn't be very far. And so what would happen is, over time, every time the engine torqued a little bit, it would eventually break that terminal. And when that terminal eventually broke, so that you'd have a good ground between the engine and the body, whenever, on that particular kind of vehicle, when it would drive off, your temperature gauge would go toward hot. And then as you stopped, it would come back. It would act almost like a speedometer. It was crazy. And so whenever I saw them doing that, I'd always look at that ground by the right front wheel, and you'd see that it was broke. And so I'd have to take a skinnier, you know, more pliable wire and make a ground, because it didn't have to be that big. But have you noticed that a lot of times your ground terminal on your leaving your battery, your ground goes directly to a bolt on the starter. You seen that? I mean, one of the bolts that goes to the starter will have that ground on it, because the starter needs a ton of ground. I mean, it needs a lot. So they're going to make a good solid ground connection to the starter directly from the battery, and that's what that's about. I mean, whenever they do that, they're doing it for a really good reason. Okay, the positive feed wires from vehicle components originated at the positive battery terminal. Now, we talk a little bit about voltage drop. Who can explain what voltage drop is? Can any of you guys do that? You've seen it before. You know what it is. You know what voltage drop is. What is it? Never mind.
It's where, say you got 12 volts at the terminal, and then a couple feet away where it's going to sensor A or some kind of solenoid, it's not getting as many because of an open or a short or
resistance or whatever, yeah. But what you're basically going to do when you're measuring voltage drop, what you're going to do is you're going to take your meter and you're going to go from the positive battery post to whatever it is that's being fed. You know what I'm saying? Whatever is connected to that. I don't care what it is. Because there's going to be a bunch of different connections in between there. And if I know for an absolute fact that, you know, we've got down there on the other end of the car even, I've got a light down there that's dim. And we can actually do voltage drop tests on the ground side and on the positive side. And if we check from the positive battery terminal, while current's flowing, we go down and we touch the other one, it's going to read a number. It shouldn't read anything if everything's like it's supposed to be. But whatever number it reads is how much we're losing. That's what voltage drop's about. You got that? So in this particular case right here, let's say that this bulb was dim. Okay, so I take my meter here and I'm setting it up here. And I'm going to look at my meter from here to there. And whatever that meter reads is how much voltage is being lost. Probably it's that switch or maybe one of the connectors. You got that? Now most of the time when there's current flowing, if you're dropping voltage, you're going to see some melted place, you know, because heat's going to happen. If it's a load carrying circuit. And the bulb is actually what we would call a load. Got it? Talk about that again in a minute. You can also measure, incidentally, if you go from the negative side of your battery to this side right here of the bulb, and you read some voltage drop there, you're allowed to have a half a volt here, but you're only allowed to have a tenth of a volt here, a voltage drop. All right. Let's see who this is. Hey, who you looking for?
Y'all ain't in class, are you?
Yes.
I was just going to ask, y'all do diagnostics?
Yeah.
Like put ECMs up?
Yeah.
Y'all do?
Yeah.
What would I do if I needed y'all to hook one up?
We do a work order and everything. Let me get through here.
Okay, I appreciate it.
All right. You guys open some doors and turn on the fan. It's hot.
What time are y'all through?
We'll be through in probably, come back in about 45 minutes.
Okay, I appreciate it.
I don't know who that guy was. Okay. Even though the ground has the excess of electrons, the positive post is the one that's generally regarded as hot. That's what people call the hot post, is the one that is on the ground side, right? So electron theory. Now you got two different theories. You got electron theory and you got conventional theory. Conventional theory says that current flows one way, and electron theory says it goes the other way. See, this is electron theory. They say it flows this way. But conventional theory says it flows the other way, positives and negatives. See, notice how they got those arrows drawn from negative to positive? I mean, with it flowing in that direction, that's electron theory. And so the current automotive circuits is usually traced from the battery source to the load bulb motor, which is conventional theory. And this is what you got showing up there is backwards to what we usually think. Doesn't really matter which way it's flowing, you just got to find out. Okay, so you got a chemical source of electricity, it's got a number of positive plates and an equal number of negative plates. Okay, so you got a positive plate and negative plate up there. See all the negative ones over there that want to get over here? All right, there you go. So which way they're flowing is not really as important as the fact that you can find out what's wrong. When positive and negative plates are in an electrolyte solution, what's an electrolyte?
Potassium, or it's just something.
What about? Well, it's something that's not balanced, which would be water's got a pH of what?
Got a pH of 7.
7, exactly right. So if you go down, you got acid. You go up, you got alkaline. Is that right? It's easy to forget one way or another. If it's going, you got now. You know you got what's in the car battery? What's in your car battery?
Sulfuric acid.
Sulfuric acid. And if you get it on your blue jeans, what happens?
You need a hole in it like this.
Yeah, it's glass. You'll see them. Right. When I was in junior college over there, when I first went and enrolled in Enterprise State Junior College, when I got out of high school in '75, I enrolled for 15 hours of college credit, paid $67. That's how much it cost in those days to go to college. Well, anyway, or to go to college at ESJC. I had this beaker of water. I was working in a photography class. There's this girl I knew named Elisa, sitting there in the student center, and I went walking through the student center with this beaker of water going from the lab to the photography thing. And I splashed a little bit of water on her blue jeans, you know. It's just water. And she goes, "What is that? What is that in that thing?" I said, "That's acid. That's the last you'll see of those blue jeans." You know? So anyway, she got all spooked about that, but it was just, when it dried up, everything was okay. All right, so electrolyte is actually anything that's out of balance. Now, how many of you know that you can take a lemon and take a little light bulb and hook 2 wires to it and stick them in the lemon and a light bulb will light up? Why does that happen? Daniel, you know? Is the lemon's acid, right?
Lemon should have a pH of like 2, I think.
Yeah, it's really low, you know, and it's about like a Coca-Cola. It's got some pretty, you know, low pH too. Yeah, you know, you can put a T-bone steak in a bowl of Coca-Cola and it'll be gone in 2 days. We're drinking that stuff, huh?
Coke also makes your bones real brittle if you drink a lot of it, because the the phosphoric acid and it gets in your bloodstream and bonds with things it needs to get to your bones.
Yeah.
You end up peeing it out instead of it going where it needs to go.
Yeah, so watch that when you're drinking your Cokes, guys. He's telling the truth. Anyway, if you've got, now what's in a regular battery, like the battery in my little flashlight here? What's in there? How do those work? What kind of batteries are these? What do they call them? Alkaline batteries. Alkaline. And what is alkaline? Alkaline is unbalanced in the other direction, right?
Basic.
Yeah. So basically, you can have a battery either way. But long and the short of it is, if your plates are submerged in a sulfuric acid, it's the acid that provides the... You know, how many of you are fooled with these HHO generators? You know what I'm talking about?
I studied them.
Yeah, where you got little plates that are interflated from one another, and you submerge them in water, you put baking soda in there, which is alkaline, right? And then whenever you put power and ground there, it flows through that. And whenever it flows through that, it makes HHO gas, which is flammable, which you're supposed to be able to pull into your car and help you with your gas mileage. Now, I don't know. You know, I put one of those one time just for the heck of it. I built one out of a mason jar and some stuff, put it on my Jeep, and it dropped my gas mileage from 21 to 17. So that was a humdinger there. Okay. When a battery is charged, chemical reaction with acid plates makes the excess electrons collect on the negative plates. Okay, if the conductor is connected, that's what I told you earlier, it's going to flow through it. You know, so that's what the deal is. Okay, now, when you got current flowing through a conductor, and actually, when you've got a conductor there, you pass a conductor through a magnetic field, you're creating energy. Now on your alternator, you know, the stator, look at this thing over here. Can you see this thing on the board? That thing right over there. That stator on that alternator has got 3 windings. And if you stretched them out, they're wound one of 2 ways. They're either touching at each corner or they're touching in one spot with 3 ends. Okay, but they're not touching each other, they're only touching in one place. Okay, they got them wrapped round, and that rotor that's in the middle of the alternator is magnetized, and it spins and it creates the power that charges your battery and keeps your car electrically fired up. And they use this induction principle to do that. So if you've got a magnetic field that's there, notice how they got a magnet north and a south pole, and they pass this piece of conductor through there, you're going to create current in that wire. I could actually show you that if I wrapped a copper wire around and hooked a voltmeter at each end, I ran a magnet through it. You'd see that happen. And so, okay. But anyway, alternators, generators, and inductive sensor. This sensor right here on this flywheel, and that sensor on that board, has got a core, and they've got, it's a magnetic core, and around that magnetic core, they've got copper wire wrapped. And every time you send a tooth wheeling past that core, it causes a voltage, sine wave to come out of that sensor, and that's the computer reads that, and that's how it moves fire those coils. All right. Now, how many of you have ever shocked anybody by walking on the carpet? You ever get anybody like that? You ever do it on purpose?
Most of the time.
Yeah. You know how much voltage is coming out of the tip of your finger when you do that?
Like 300,000.
8 to 25,000 volts, actually. 8 to 25,000 volts. That is pretty strong, guys. That's a pretty good bit. Now, when I used to be on the treadmill, you know, we used to do a treadmill before we, wore the thing out and everything. And I'd be walking on the treadmill, my wife would come by and I'd touch her on the ear. His computer would slap my face, because but you could charge up yourself big time, All right, so anyway, that's that. So my brother-in-law, Gary, took his picture of his lightning. He's a photographer, and I borrowed that picture from him. Okay, now then, we got some electrical circuits here. You got right here, electrical circuits, a complete pass for current flow. You got to have both sides, right? I've seen people just hook the positive up and they wonder why it won't work because they never hooked up the ground. That's not a good way to go here. Okay, defined as being from a power source to a load component that has resistance and uses electricity to do its work. The work is actually being done by electricity. Now, how many of you know about the first law of thermodynamics? You know what that is? You can trade matter for energy. You're going to burn wood to get heat, right? You're going to burn gas to get heat and power and that kind of stuff. Now, you're never going to get back as much as you put in. Something's always lost. The second law of thermodynamics. also says that heat's going to travel from, you know, cold, from heat to cold. See, heat flows, not cold. All right, but at the same time, there's a bunch of other ways that's manifested too. If I start a bicycle wheel spinning and I let go of it, it's going to stop, isn't it? You got to keep putting energy into it to keep it going. And because Sean had all these crazy ideas about perpetual motion, we ought to be able to make a generator that makes it charges up something, and so it just runs all the time and it never wears out. Well, that's really been tried by forever, and it just doesn't work. You always got to put something in to get something back. But whatever you're putting in, you're going to get less back than what you put in. With your car, or you're only 20% of that energy is being used to propel you down the road. Where's the rest of it going? Heat goes out the pipe and through the cooling system and all that. I mean, it seems to us like it works fairly efficiently, and it's not polluting the air because CO2 ain't hurting the daggone thing. You know, but at the same time, you've got to put more in than you're going to get out. So that's why you have to empty your wallet into your gas tank to go to the beach or whatever. See what I'm saying? All right. So one component, there's your battery. Now, don't we all just love these side post GM batteries?
No.
Don't they? That's that wonderful stuff, you know? Particularly the one where they run this long bolt through two of these cables. There's all kinds of potential for corrosion in there and everything, and it can look just fine and be so crummy that there's no way that it'll ever. So, now let's know what it says here. The power source is the battery when the engine's switched off, and the alternator when the engine's running. See, that's pretty cool. Now, what is this over here? This right here is the symbol for a battery on a wiring schematic. When you see that on a wiring schematic, you're going to see a battery, right? Conductors are wires and cables, and they're usually protected from each other by insulation. Even on those copper-looking wires that you have in a motor, those wires have got shellac of some, you know, that keeps the wire from touching other coils that it's next to. This is a car that I actually fixed. You see this little place right here? That right there got against the hot place on the EGR valve, and it was actually going to the alternator to tell it to charge, and I had a trouble code I was fixing with that. But it kind of burned that. That's when I took that picture. It burned all that split loom off, and it shorted that to ground. That's basically where that picture came from. But in an automotive circuit, the vehicle chassis and engine block are conductors in the circuit. Okay, let me ask you this. What if I take my Tesla out here? Which I have one over here. All right, I take my Tesla out. And my Tesla, you know, you hook it to the battery, and then you hook it to, if this thing right here was hooked up to power, and I hook this to ground, and I touch this big wire coming from the alternator, it should be hot. Right? Okay, so let's say that I go to start the car, and it doesn't do anything. Okay, and they say, we've already replaced the battery with a brand new battery, and it still doesn't do anything. So I get my Tesla out and I hook it from here to the other side of the battery, and it lights up really good. So then I hook up to the negative side of the battery. You got it? And then we turn and I hear a click on the starter relay, but nothing really happens as far as this engine spinning over. And I touch this, and the light lights up. Now I'm hooked to the negative side of the battery, and I'm touching this metal on the engine, and this light lights up really bright. What's wrong?
It ain't grounded.
Huh?
It ain't grounded.
Which what?
The engine block.
Yeah, the engine block is not grounded to the battery. You'd be surprised how often you see stuff like that. And the reason, how do you know it's not grounded? What's the explanation for the light coming on?
Because I could have looked up negative, it should show positive, like energy coming from it.
Should go through the engine block instead of the test line. The only path to ground it has is through this little bulb. And the starter's not going to spin if it's going through the bulb. It's got to go through the engine block. It's not making it to the engine block. There. Okay, this right here, here's your switches. You got to have a switch. This is basic stuff. Notice how I took this right here. This is got the wrong pointer. This bulb right here, and that bulb right there. This is actually a bulb in a schematic, and that's a bulb in my hand, and that's a motor in a schematic, and that's a motor in my hand. Well, those are a device that uses up electricity and turns it into work. Light bulbs and motors use every bit of the power unless they're wired in series, and then if a bulb and a motor is wired in series, the motor is probably not going to run unless it's a real tiny motor. The bulb will. The circuit protector is a device. That's a fuse. That's what a fuse looks like, basically. There's a couple of different variations of it. That's a fuse. That's what it looks like on a car. Got it? Alright, current will flow if the switch is closed, the circuit protector is not open, and charge is available. Ohm's law is a basic rule for relationship between voltage, current, and resistance. Now, you guys familiar with Ohm's law? You can tell me about Ohm's law. Anybody know about Ohm's law? This is not anything you'll ever use to fix anything, but everybody needs to know and understand Ohm's law. And Ohm's law is simple to learn. It's not a big deal. It's just simple division. Okay, an increase in voltage will cause an increase in current. Now, this is going to confuse you if you're not really careful, particularly if you've worked in the air conditioning refrigeration field or somewhere like that. Now, why is it confusing? Because if I've got an air conditioner, I've got it in my window, I've got a window unit air conditioner, and I don't want my power bill to be really high, am I going to have a 220 or a 110 unit? 220. Higher, yeah, the higher voltage. You're only going to use half as many amps with with a unit that's made to run on 220. Got it? Because you got twice as much voltage, and it takes half as much amperage to do the work if you got twice as much voltage because of the extra push. You see where I'm going with that? Okay. Voltage is in effect electrical pressure. The higher the voltage, the higher the pressure. So 1 volt pushes 1 amp through 1 ohm. That is Ohm's law right there. That's where all those measurements came from. How do they come up with volts, amps, and ohms? Okay. Current flow is inversely proportional to resistance. Now, if you understand big words, what you'll recognize is an increase in resistance will cause a decrease in current flow. They go opposite directions if you look at them on the graph. Got it? High current flow, look at a water hose. That was my boot there. Added resistance. Low current flow. See, I got more coming there, less coming there, because my boot's on the hose. Right? I've added some resistance. Consider this as voltage. I mean, the flow is amps, voltage is pressure, and my boot's the resistance. Okay? See this? EIR. E is volts, I is current, R is resistance. Voltage equals current times resistance. Voltage equals current times resistance. Okay? 1 volt pushes 1 amp through 1 ohm. So how many amps will 12 volts push through 6 ohms? Somebody tell me. That's ohms. That's amps. Got it? Current flow, 2 amps. You notice how this ammeter is wired up? The ammeter is wired up so that the current is flowing through it. We're going to be doing some of that kind of stuff in electrical. Resistance, 2 ohms, draw 5 amps. Resistance, 2 ohms, draw 6 amps. You only got 10 volts here. See that? Weak battery, nothing much amperage there. Alright. Okay, voltage is like pressure. Increase in voltage will always increase current draw. Now, that is one of the things that is true in automotive circuits, but it's, like I say, if you're talking about alternating current and house wiring and this kind of stuff, that's slightly different than this. So don't let that confuse you. This is a different thing from house wiring. Car wiring is not the same. This is something, and this stuff right here, you know, is something you just got to current and voltage and all that kind of stuff. Once you sort of get used to it, you get where you understand it better. But sometimes when you think you understand it really, really well, something will come along and challenge what you believe. So keep an open mind on this stuff. This right here is basically automotive specific. Voltage is expressed as a difference in potential when it refers to electromotive force caused by difference in electrical charges, blah, 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 blah. So 24 volts difference in potential. Whenever it used to years ago, and don't ever try this nowadays because you'll fry everything on the car. If we had one that was spinning really slow, sometimes when somebody has tried to start an engine and fuel keeps squirting in there, it washes the cylinder walls down on one of these older vehicles that's got the high tension piston rings. Have you ever heard one that somebody's trying to start, it's been sitting up a long time, or they try to start, it won't start, and it's going, it just turns real slow, and you're sitting there saying, what is up with this? You know, I mean, whenever you're driving a car every day, it goes, fires that up. Well, it turns real slow. What I used to have to do, like the old guy came to get me one day to start his irrigation engine down there by his pond, you know, 6 o'clock Sunday morning, he's knocking on the door, can you go help me get my irrigation engine started? So I went down there, and it had been setting up, and the cylinder walls had, dried. I mean, the oil was off of it, so the rings were dragging. So I put points and plugs in after we chased the wasp and the rattlesnakes away. And then so he had just points. I mean, there's no electronics to worry about on this, you know what I'm saying? And so I took the positive battery terminal off, right? and I hook my jumper cables up. See, at my negative battery terminal, see, I've got jumper cables in my hand, right? Okay, his battery's pretty strong, but it just can't spin it over fast enough to get it going. And so I took the positive battery terminal off. And what have I got here now sticking up where I took the positive battery terminal off? I got the positive cable was hooked to the positive battery terminal. I'm going to hook the negative cable to the positive battery terminal on his battery. Are we together now?
Go for it, keep going.
And then I'm going to hook the positive to his positive terminal. And then I'm going to hook the other two cables together. So I've got one going from the negative battery terminal on the vehicle to the positive terminal on his battery. And then that other cable, anyway, I've hooked the batteries in series, you see. And so that puts 24 volts in the starter. And boy, does it ever spin that thing fast. Fire it right up. Scares the stew out of somebody when they see you do all that. But if you do it on anything that's newer than about a 70 model, you're going to fry a bunch of stuff. Now you got to be really careful not to do this ever, unless you're working on something like a dadgum old diesel tractor that ain't got no electronics on it. You see what I'm saying? But that changed it. I used to have a 24-volt Jeep battery. It was a military Jeep battery that I carried around in my trunk. And you could jump off anybody with that darn thing. Well, just spin the stew out of it. All right. Okay. Current flow of electrons between 2 points. Look at this right here. What kind of circuit is this? Parallel circuit. You got it? Why is that circuit parallel? You can blow that bulb or that bulb, and the other bulb will still stay because each one's got its own ground, right? Ground here, ground there. Each bulb's got a dedicated ground. But this one's got 2 amp draw, and this has got 1 amp draw. Got more resistance in that one. Which is going to be the brightest bulb? The one that's pulling more amps is typically going to be the brightest bulb, yeah. So anyway, you got 3 amps draw. But load A, load B. There's 2 different loads. You got 2 amp versus 1 amp. Okay. All right. Excuse me. The unit of measurement to determine current flow is ammeter, and that is the movement of 1 coulomb of electrons past a given point. A coulomb is a billion electrons. That's a lot, isn't it? You gonna remember that word? C-O-U-L-O-M-B. That's a good Scrabble word, huh? C-O-U-L-O-M-B. Coulomb. Remember that word? That's a billion electrons. Now look at this. 1 amp is a movement of 1 coulomb of electrons past a given point in 1 second. Now, how do they count those? I don't know. All right. Current's the measure of a rate of electrical flow, and it can also be known as amperage draw and is measured with an ammeter. Okay, when 2 loads are connected parallel, each one draws current independently, and I'm not going to go there, keep going with that. And the total current draw to parallel circuit equals the sum of individual current draws. All right, but look at this series circuit. Look at the difference. You see a series circuit. Everything is leaving. This is actually wired in series too. So this is actually wired in series, that and that. You take any of these out, and you've lost them all. All right? But their combined resistance will be 18 ohms. See that? Combined resistance, 6 ohms, 12 ohms equals 18, because they're in series. All right, look at this. 0.67 amps times 18 ohms equals 12 ohms. See how that figures? How that works? You got it? Everybody understand that? There's your little, sometimes they'll use a circle to do this instead of a triangle. All right, there's your resistance. All right, have you seen something like this before? What would you call that? This is actually, have you ever turned the knob to dim and brighten your headlamps? Huh? That's what that is right there. That's got a little set of points dragging on that resistor wire and all that. But resistance in opposition to current flow is offered by a load resistor. Now, why is this here thing made out of white ceramic?
Ceramics, it won't conduct.
No, it won't, but what can it handle that almost nothing else can?
A lot of heat.
A lot of heat. I was at a school in Covington, Louisiana for Chrysler, and the instructor, I don't know where he came from, but he made the remark that resistance didn't make heat or something like that. And every mechanic in there rolled their eyes because they knew better than that. And so nobody wanted to take him on, but I took him on. And the thing about it was, I said, why do they make resistors out of ceramic to handle all that heat if resistors don't make heat? I don't know what in the world was going on in his mind about that. That's just crazy. But anyway, you're going to have heat where you've got resistance. I mean, the bulb gets hot whenever, your light bulb does. Conductors have some resistance. A piece of 22 gauge copper wire 60 feet long has 1 ohm of resistance. 60 feet is how far? Maybe from that wall to the other end of the shop or something? More or less. Heat causes resistance. And look at this. You seen something like this? Anybody seen anything like that? Where they burns up these terminals? It starts to develop oxidation, and that's resistance. That makes heat, and that makes more oxidation, and it just continues to heat up until you wind up with a nasty mess. Every connection's got some resistance, and that's a snowball effect. That right there is a blower motor relay off of a Oldsmobile, and it came in. The blower wasn't working. When you unplug that, this is what we found. You got to replace the relay. You got to replace that connector. Pigtail. All right. When the resistors in series, the total resistance is 6 plus 6 equals 12. Right. But look at here. How many is here? Somebody tell me.
6.
6. Is there? How much is there? Back to electrical. He needs to know that. How much resistance will this circuit here have? I took my meter and I put it right here and right here. What would I read? That's spooky, isn't it? What do you think? Somebody guess. Just give me a guess.
3.
3 is good. 3 is a good answer. Why do we have 3?
You said yes, you just said why.
Well, I'm just asking you. You were right. Why do you? But why would you have 3? If you got 6 and 6,
resists, so
huh?
half of 6 is 3.
He's thinking clearly. That's exactly right. Basically, if you think of each resistor like of a low resistor, like if a resistor of 1 ohm would be like a big hole in a bucket, and a resistor that had a lot of ohms would be like a little hole in a bucket. So 2 6 ohm holes is equal to 1 3 ohm hole, which is twice as big. See that? You're basically doubling the size of the hole. There's another place for current to go. So you got only half as much resistance, you see. All right. So with a 12 volt supply, how much amperage would each of these resistors pull? That's pretty confusing, isn't it? Okay, so you got 12 volt, 6 ohms, how many amps? 2. Each one's going to pull 2 amps, so 2 plus 2 equals 4. So you're going to be pulling 4 amps with that one. See that? If the total circuit pulls 4 amps, how many ohms of resistance would the total circuit have based on a 12 volt supply? See, 4 amps. See how that works? You got that? 3 ohms. 4 amps. See how you can figure that out? Okay. With a 12 volt source, how much would the total resistance with this parallel circuit have? Gets more complicated when the numbers aren't easy, doesn't it? When they're not both the same. He says 2. Let's see where he comes from. 5 amps. 2.4. You were more far off. See that? That's how you do that. Okay, so resistance in parallel is 2.4 ohms.
How do you get 2.4?
Well, watch this. You're going to take these right here. Okay, what's 4 plus 6? 10. Huh?
10.
Okay, so what's 4 times 6?
24.
You got it? 4 plus 6 and 4 times 6. 2.4. You see where that formula, how that formula works? Okay, so you're going to take 4 times this, and you're going to put it over 4 plus this, and you're going to wind up 2.4. So how many times will the sum go into the, what do you call that? The product? Yeah, whenever you multiply something, you call it the product. So how many times will the sum go into the product? That's how you get that. And that comes to 2.4. He asked a good question. Where'd you get that? How'd you get there? Okay. Basic rule for closed circuits that voltage used up or dropped in the loads is going to be equal to source voltage. That is an important question. You're going to see that on test center later. The closed circuits use up or drop every bit of that voltage. So basically, if you read 12 volts here, you're going to read 12 volts here. You're not actually going to have anything less than 12 volts there. This is going to drop every bit of that. Now you can actually go from here to here. Let's say that you measured right here and you had 12 volts. You measured over here, you had 10 volts. That means you're losing, either you're losing 2 down here or maybe 1 here and 1 there. But you're going to be losing something. Measuring voltage drop would be to put it here and here with the current flowing. And if you read 1 volt, you're going to get 1 volt less over there because some of it is going to turn it into heat and burning up your switch. All right, the voltmeter at point A is going to measure source voltage. So the voltage at point B is what? You're actually looking at, see, ground? Voltage at point B should be 0. Okay, 12 times 0, which comes to 0 volts. So here we go. When 2 or more loads are in series, you got brightness control of your lights. See that? The voltage drop is equal to current draw times resistance. E equal I times R. That's the sum of all voltage drops equals source voltage. Always does. I mean, it's always going to be the whole, all of these over here is going to equal 12 volt drop. I'm going to change the battery in my laser. I'll use that green light I got showing. Okay, move your probe to the ground side circuit. If you move it closer and closer, you're going to see lower and lower voltage as you go downhill. Got that? Don't get bored with this because you're going to have to know it. Okay, now then, this is an important thing. Here, Ohm's law is not quite as important as this. Okay, your available voltage at each point. See, at A, B, and C. 12 volts, 6 volts, 0 volts. Total resistance is 6 ohms and it draws 2 amps. We're going to, okay, the voltage drop at the brightness control is 2 amps times 3 ohms and that equals 6 volts. This is all confusing. But see when we're moving our meter, you can tell I did that with a live wire, can't you? Okay. See this? Look at that. What you got there? Resistance. You got 12, 12, 12, 12. If all the resistances are equal, divide the resistance of one alone by the number of resistors. See that? 12 divided by 4 equals 3 ohms for the total circuit. You got that? Everybody? Okay, so you got unequal resistance. Multiply and divide by the sum. That's what I showed you earlier. So 6 times 12 is 72. 6 times 12 equals 18. It's 4 ohms. 18 into 72 is 4, right? Everybody know that? Are you good with math? 18 into 72 is 4. Right? I'm hurrying, guys, trying to get through this. Okay. Okay, I'm not going to spend a heck of a lot of time on all that nonsense. Okay, the storage battery provides current to all electrical systems when the key is on. Now, what is this right here? Look at this. This is a schematic drawing of an alternator. Notice you got, these are diodes. Is this the first time you've seen a diode? Anybody seen a diode before? You know what a diode is? It's a diode right here. All right, now this right here is these little slip rings on the rotor that spin in the middle. And this is this little Y wound stator is actually represented by that. And then this right here is grounded. Okay. So anyway, for what it's worth, that's what you're looking at. Case grounds are used for the components attached to the well-grounded part of the vehicle. Some relays are made like that. They got a metal ear on them, a hooked thing. Remote grounds are used where the component's not grounded. So you're going to have a light that's, a wire leaving the license lamp light and going over here to ground somewhere. You can control a component with a remote ground, like reversible motors and power door locks, like we did earlier. Okay, let's read the schematics here. Okay. Now we're going to go to this right here. Diagrams, picture rangers, transmission controls. All right. Yeah, don't worry about a lot of that. We got some of this system on some of our machines out here, but I spent more time on that than I should have. But on the top of the schematic is hot. Fuse is up there, the ground is down here. It typically flows down. Occasionally they have trouble drawing a schematic like that, but in just about every case you're going to see that. Now this is really, really important. From this point on, watch this, because this is going to help you an awful lot more than you think. Okay? Now then, power is fed to the fuse. Well, why don't we got this stupid input thing up here? Okay, we're going to start tracing power to ground. All right, down here, we're going through C172. You see that? We got to find C172 through circuit 295. Now, a connector is C172 is a connector. Now, watch this. Okay, most of them have got a wiring location like that. You see C172 on there anywhere? Huh?
Top middle.
Top middle. There it is. See that connector? All right. Using the numbers and letters at A6. A6. All right. And then you can also pull up an inline picture of that connector. Notice that C172F is on the left, and this is female, that's male, And on the right, these are mating connectors, right? Okay, so, okay, where's circuit 295? You see this table down here? See circuit 295 anywhere? Anybody see it? Is it in this column, that one, or that one?
On the right side.
Right there, isn't it? It's light blue pink, pin 34. All right. So, you're going to locate the wire where it goes in the connector. We know where C172 is. Okay. We know what the connector pinout looks like, and we actually know that pin 34 is that one right there. So now we can go to that one connector and take it apart, and we know exactly what pin we're looking at. See what I mean? That's how you find wiring problems and fix them. Okay. We should notice about this current path. This one right here means that it could have either one or two switches depending on whether it's manual or automatic transmission. That's an alternate current path. See that thing up there? When you see it coming in from here and going this way and that, you know if it's automatic it's this and be the other way. Okay, the wires going into and out of the switch both have pass-through connector C172. In other words, going in and coming out. It's going through the same connector. So basically, you know, they go to their destination to do that. After the circuit passes through the switch, the circuit number changes from 295 to 140. Now, see there? It's black pink. It was light blue pink. See, it's changed colors. Okay. Connector pin out. Circuit number 140 is where? Can you see it? Anybody find a 140?
On the right. Back to BK and BK.
I don't even see it my own self. Oh, there it is. Yes. That's it. It's just two. It's on pin 32. All right, pin 32. Those two pins are the ones we're concerned with. Part of the backup lamps. Okay. This circuit passes through a splice and two more connectors. The splice could be the problem, and that's usually taped into the harness. It's going to be difficult to locate, so you examine that last. So let's find connector C148 in our location drawing. You see a C148? Right there? Got it? D10 on the grid. Alright. Now, circuit 140 and double check the wire color to make sure we're still on track. Write down the pin number. Where's circuit 140?
On the left. On the right side of the left thing.
Yeah. It's also there. See that? It's in, this is both sides of that connector. So you notice that it's actually the pin 13, isn't it? Pin 13 there, pin 13 there. Write down the pin number. Find that connector on the vehicle. Let's go to see if we can find 411. That one right there the same way. Where's 411? Got that? See 411. Alright. The circuit we're looking for, this is a different connector. This is the one at the back. See? The one that we found back here looks like this right here. So we're going to write down the pin number. We can go to that connector, find the pin in question, check the circuit. Our last connector is C403. We're going to find it on the vehicle like we did the others, and it's right there. And the circuit number we're looking for is still 140. You got that? 140. Okay, see, because of the fact that you know the problem is on that particular wire, you need to be able to track that wire everywhere it goes. That's what you're doing, basically. That right there, what I just showed you guys, is probably the most important part of this whole presentation, because that's how you're going to find and fix a problem. You got it? All right. Yes, it is. One more potential problem is the ground. Let's locate the ground. Where's G104? Look at this. Why in the world is the tag light ground up there behind the daggum headlights? And the tag light's on the other end of the car. Look how long the wire looks. But you notice you got little broken parts of that wire? That means that it goes other places besides just there. There's obviously other things that depend on that ground. But this is the ground for the tag lights? Isn't that crazy?
It's a Toyota because it's more complicated.
Wow. All right. Okay, now, that's what I was talking about right there. Okay, this right here is your GM schematics and so on and so forth. And they work pretty much the same way, but notice how they look a little different from the Ford ones? Every manufacturer has got schematics that you can figure out if you know how schematics work, but they're going to look slightly different. GM's got hot buttons on the schematics, and you got to go to here and here and here and look at your engine component views, and you're going to find the connector that way. See that? And that was it. That was all. There you go. Just wanted to kind of expose you to some of that stuff real quick. That right there was something that is kind of on the